Hi everybody, welcome to another video in Calculus 3, section 16.6, integrals for mass calculation. So this is an application of double and triple integral. It is going to be a long section. Right, center of mass in one dimension. So we have an example here. Suppose there's a much bigger mass and a little smaller mass, and if we want to balance it, the bigger mass has to stand closer, and then the smaller mass can stand further, or the center of mass tend to go closer to the bigger mass. And the formula for the center of mass, this is only in one dimension, is the mass times all the coordinates over the total mass. The sum of the mass times the coordinate over the total mass. And this, each one of them is the moment, and we add all of them up, the sum of all the moment. Right, now we have an example here. We have 1, 2, 3, 4 of them at 4 different coordinates. Now we're trying to find the center of mass. So this is pretty straightforward. There are 4 of them, right? So the center of mass denoted by x bar. We will have m1 x1 plus m2 x2 plus m3 x3, and since there's only 4 of them, we can just write them all out over the total mass. Right, so mass, the total mass is m1 3, the distance negative 1.2, the coordinates negative 1.2, mass 2, 8 times negative 0.4, mass number 3 is 1 times 0.5, and then 6 times 1.1 over the total mass 3 plus 8 plus 1 plus 6. Right, I'm just going to put all of them in the calculator. Fraction 3 times negative 1.2 plus 8 times negative 0.4 plus 0.5 plus 6.6. Again, just type. Yeah. And then 3, 8, 11, 12, 18. Which convert to fraction 1 over 16. So pretty straightforward. One dimension, that's all we have. So let's just write out the formula. I mean, one example is good enough. Now, this is the system of finite mass. I mean, finite number of masses. Now, if we want to do this, let's roll beyond. Now, instead of bunch of isolated masses, now we consider one big object. It could have irregular shape. Now, but it is in one dimension, so we might consider, instead of an isolated point, we have a thin rod. So that's, of course, one dimension is not really interesting. It can only be a thin rod. It cannot be anything else. Or Y. Yeah, so the thickness is negligible. Right. let rho be the density. So we have density and then the center of mass is given by this formula. So the moment m and the mass m. So the only difference between this formula is the moment they have the distance times it. Right. So just a little physics. Mass is equal to density. Depends on we talk about the mass of a wire, or mass of a thin rod, a mass of a thin plate, or a mass of an object. So that could be multiplied by either length. If we talk about the mass of a thin rod or a wire or of a thin plate, so we can have density times the area. So density here could be in terms of unit of mass over the unit of length, or area, or could be volume. Depends on what type of density we have. Density could be mass over length, mass over area, or mass over volume. But that's what we have. In this case, 1 dimension it is length, 2 dimension is the area, and 3 dimension is the volume. Right. And the moment is equal to mass times the distance. Right. I said not much in 1 dimension. We just have a thin rod or a wire. And that's all we have. And the density, think about this. The density acting like, consider you have a piece of wire. Because it might be difficult to imagine that the mass is different on the different point on the wire. But think about this. Let's say instead of talking about mass, we can talk about temperature. If you burn real hot on one end, because the heat will transfer that, right? So at each point there will be a different temperature, right? And just like each one of them has a different density at different point. So like I said, each one has different density. So when we do that, the summation, density times length give us the mass. So that's about that. Right. Now we go to 2 dimension. Center of mass of 2 dimension. So let rho be the density. So we still have a density function. Over a closed boundary region. Now this is density function over R2. So this is a density for an area. The coordinate of the center of mass. So because it is 2 dimension, we have the x bar and y bar, and that is the coordinate of the center of mass. And given by the mass is the density times the area. Moment mx is equal to that, and my equal to that. So what is the deal where we say x bar and we use my, but then my we have to multiply by x? So what's that about? Right. Think about this. I have a coordinate system. This point here, the distance to the x-axis is the y values, and the distance to the y-axis is the x values, right? So the moment my is the moment about the y-axis. We multiply by x because that is the distance about the y-axis. So we're not talking about the point. So we have a bunch of points, and we just have the mass at that point times the distance to the y-axis. So the moment about the y-axis is given by this. And then the x bar is the moment on the y-axis divided by m, and then moment about the x-axis divided by m give us the y bar coordinate, right? So this is not backward. Moment about the y-axis multiplied by x to it. Now, y is the x bar is my over m. So we're not talking about just a point. Now just consider, we'll not consider the two-dimensional object, just consider a few points. We have a mass there, m1. Here m2. Of course, with that we have the distance to the y-axis, x2, and distance to the y-axis, x1. So the total moment about the y-axis, the system of two objects here, is m1 x1 plus m2 x2. When we do that and divide by the mass m, we have the center of mass on the x-axis, so it will be somewhere in the middle here. If we don't talk about the x-coordinate, the y-coordinate, we'll worry about that later. But the center of mass will lie on this line, which is x bar, right? So our moment in the about the y-axis divided by m give us x bar. So the formula is not backward, it's makes perfect sense. We need all the moment about the y-axis, sum of all that divided by mass, to get the average values for x. Right, now let's go to the example. The reason this is a long section because you see each example occupy the whole page, so look like a long problem. So find the centroid. Oh wait, before we go to example, we define a centroid is the center of mass whose density is constant. So centroid is just a center of mass where density is equal to constant. If it is equal to constant, we just assume that to be 1. Or we can just put a constant there. It doesn't matter. I'm just going to write this real quick. If we have mass, double integral density, which is now a constant. Actually, I will not write anything else. dA, that gives us the mass. And then the moment about the y-axis, we're going to stick an x to it. And then over. So you divide them. Since this is constant, you can just take it outside. And then we have moment about the y-axis divided by m. The rho and the rho cancel out. So when we talk about the centroid, we just say the density is equal to constant. Or for simplicity, we let density equal to 0. I mean equal to 1. Sorry. So density is constant. For simplicity, we can let density equal to 1. For calculation, it is easier if we just let that equal to 1, because when we divide them, that will cancel out. However, if that is for the center of mass, yes, but if you want the mass, you might want to just put a constant there. Yeah. If we calculate center of mass, that is not a problem. If we want the mass, it might be a problem. So just if we calculate center of mass, if we just calculate the mass, just keep the density. But for now, I'm going to keep the density, and you will see it doesn't really matter at all. I find the centroid of this shape. bounded by those two functions and then the y-axis. So simple enough. So first we set up the formula to calculate the mass, and after that we find the moment about the x-axis, the moment about the y-axis, and then find the center of mass. Right. So first calculate the mass. Density is constant. So centroid meaning density constant. So I have density constant and times dA. Over the region R. So in general, that's the most fundamental thing. Now, obviously, this when we set up the limit, the easy way to is set up dy in the middle and then dx. If we look in that direction, we see this function first, and then we see the other function. So bottom function, top function. So we go from the bottom is 1/2 minus e to the negative x. Y equal to, and on the top, y equal to e to negative x minus 1/2. The density is a constant, dA. The limit on the outside go from 0 to ln of 2. Cannot use Fubini theorems here because the limits are not constant, and there's x in it, so too bad. The rho is constant. I will take it outside. Integral for x from 0 to ln of 2, and sorry, it's not the a anymore. Once we specifically write y inside and x outside, the integral will be dy then dx. Now integral of dy, there's integral with respect to y, there's nothing here, so they just be y, and going from 1/2 minus e to negative x to e to negative x minus 1/2, and then dx. Yeah. So inside we just have that, which the rho is a constant. Now y, we substitute that in, and we subtract them. E to negative x minus 1/2 minus 1/2 minus e to negative x dx. Right, e to negative x, negative and negative, make that two of them. Negative 1/2, negative 1/2. Negative 1/2, negative 1/2 is negative 1 dx. Right, integrate this. We have rho e to negative x is 2 e to negative x over negative 1. Integral of negative 1 is just negative x, and we'll go from 0 to ln of 2. Right, so that gives us rho times negative 2 e to negative x minus x 0 to ln of 2. I put in ln of 2, rho negative 2 e to ln of 2 e to the negative ln of 2 minus ln of 2, subtract negative 2 e do negative 0 minus 0. Right. I hate to take a lot of space here, but yeah, let's just worry about space later. Right. E to negative, I would take the negative here, put inside that. So I have negative 2 e to the ln 2 to the negative 1. Minus ln of 2 e to 0 power is 1 minus negative 2, so that is plus 2. The row multiplied by the whole thing, right? So we have row E and ln cancel out. Just keep doing that. So we have negative 2 times 2 to negative 1 is 1/2 minus ln of 2 and then plus 2. So that cancels out, is negative 1 plus 2 is 1. So row times negative 1 plus 2 is 1 minus ln of 2. Right. So that is the mass. Now go to the moment. Moment. Right. This is capital M. For x, moment about the x-axis, we're going to stick the y to it. And we still have density, dy dx. So this integral, I'll use the same integral, but I just stick the y to it. 0 to ln of 2, 1/2 minus e to negative x, e to negative x minus 1/2. Right, integral inside. The row is constant. I will take it outside of the double integral. Integral of y will be y squared over 2. And inside, I have e to negative x minus 1/2. And then 1/2 minus e to negative x. Whatever we have is dx. Right. This is not a very good first example, regardless. So that's 1/2. Right. But put that in here square. And then subtract when put in the lower limit. Dx. Right. Once again, the moment about the x-axis, we stick the y to it. Right. Actually, there's the 1/2 here, right? Just take it outside of the integral. Now just multiply this out. I'll run out of space, so when we multiply that, we have a squared minus 2ab plus b squared. If we multiply it out, that's what we have, and that's what we use. So e to the negative x square is e to the negative 2x, right? When we multiply, when we have the power 2, not the power, we multiply the powers, multiply the exponents. So I have e to the negative 2x and then minus 2ab, those two times together, and then plus b squared, and then subtract a squared minus 2 a b plus b squared. These two are identical actually. So you see there's a plus, subtract, that cancel out. Negative 2 e to the x times 1/2, negative 2 e to the negative x times 1/2. This is minus negative, negative, the plus, so minus and the plus cancel out. 1/4 minus 1/4. So this is just 0. Of course, that's going to be 0. Now, did that make sense though? Now think about this. This region is symmetric. The density is constant. That's a big deal. If density is not constant, then we won't be able to tell that. Yes, but because it is symmetric, the moment about the x-axis will have to balance out. When there's a point on the top, we cancel with the point at the bottom. The mass will be the same because the density are the same. The density are constant. The distance, one positive, one negative. So those cancel out. So the moment about the x-axis should be equal to 0 because it is symmetric with respect to the x-axis. And the density is constant. If the density is not constant, we cannot use symmetry. But because this is symmetry about the x-axis, this is equal to 0. So it's not that bad. Now calculate the moment about the y-axis. Now this is bad. Now for the moment about the y-axis, we will stick the x to it. And then rho dy dx. Moment with respect to moment about the y-axis, we stick an x to it. Now, there are almost something similar to this, because this x is a constant with respect to y, right? So earlier we did calculate that, and this is what we have here. We can even simplify to this, right? So if we integrate inside, think about this. Now focus on the integral inside. Rho is a constant. Take it outside. That doesn't matter. But when integrate that, will equal to this. Sorry, I circled the wrong one. What I mean to circle is this. And then rho. Right? So the inside, when we integrate, we will have that. Of course, there rho. So when we integrate the inside, because here adding x, it just adding a constant with respect to y. So they should not change much. Everything inside, it's just 2e to negative x, negative 1. When we integrate, except for so when we integrate inside, That's what it is equal to. X and rho is constant. We just roll it in there, into that. Rho is constant. Take it outside. And we have x 2e to negative x minus 1. Now this is still bad because x and e to negative x, that is integration by parts. I will multiply it out though. Rho 0 to ln of 2. Yeah, hopefully the remaining problem in this section is not this long. So I have 2 x e to negative x minus x dx. Alright. I will split this. We split that. Right, integration by parts. This is simple. I'm not going to use the table. Integration by part. U dv equal to uv minus integral v du. That is integration by parts. Now we will let u be 2x, is because the derivative of that is easy to do. And then this is dv, because the integral of that is doable. So scratch paper, scratch work here. U is 2x, u prime 2, dv e to negative x dx, v integral of that is negative e to negative x. Right. So integrate the integral. We have uv uv negative 2x e to negative x uv minus integral of u of v du, sorry, v v du. When we done with the integral, evaluate from 0 to ln of 2. And then this gives us just x squared over 2, or from 0 to ln of 2. Right. Now integral of this negative integral of 2e to the x is negative 2e to negative x. Yeah, there's a 2 inside, negative cancel. Integral of e to negative x is negative e to negative x, and we evaluate from 0 to ln of 2. Now this is 1/2 rho and then we put ln square, ln2 square, and then put in 0, we have nothing. Right. Now we have rho. Put in the ln of 2. We have negative 2 ln of 2 e to negative ln of 2. That's where we put ln of 2 in it. Minus 2 e to negative ln of 2. So that's where we put ln of 2 in it. Now put in 0. Put in 0. The first one is equal to 0 because there's a 0 here. Put in 0 in here, we have and then we have this term 1/2 rho ln 2 square. That term. Right. I know this is a long problem. I tried to write a bit smaller already, but right. So we did say that e to ln of negative ln of 2. What was that? Is e to ln of 2 to negative 1. That cancels out. 2 to negative 1 is 1/2. So we have negative 2 times ln of 2 times 1/2 minus 2 times 1/2 minus that plus 2 and then minus e to 0 power is 1. Actually, we just write that as 2. And then minus 1/2 rho. Forgot the rho here. 1/2 rho ln of 2 square. There's a rho. Right. Simplify all of this. Yeah. In fact, I'm going to keep the 2 here for a reason. Just factor out the rho. See what happens. Right. If you factor out the rho, this is negative 1 plus 2 negative 1 plus 2, so plus 1, right? So it's 1 minus 2. There's a reason I left the 2 there. And this one factor out the rho. And that's subtract 1/2 ln of 2 square. Right. So that's what we have. Sorry, this is the long problem. I have to pause and check the calculation. Everything's correct. Right. So run out of space, but this is the moment with respect to y. And finally, if we want to put it back into calculation, x bar is equal to the moment with respect about the y-axis over m. So we're going to x bar, the moment is going to be this. So we're going to take this, divide by this. Yeah, can't even fit in one page. So I'm going to type that, divide by that. The row and the row cancel out. So just enter one big fraction. We have 1 minus 2 and 1/2 cancel out, so minus ln of 2. And then minus, yeah, I have to pause the video in the middle to check the math. I don't want to waste time on the video to check the calculation. Everything's correct though. Divide by 1 minus ln of 2. So about 0.217. And then y bar is mx, moment about the x-axis, over m. This is 0 because the moment about the x-axis is 0. So yes. So the point is x coordinate is about 0.2 something and y coordinate is equal to 0, which makes sense because this one is symmetry. Right. Like I said before, the point here is just the concept of how do we do how to find the center of mass. So you should not expect a long problem like this on the test. So something a lot more doable than this. But the concept is pretty simple. We have mass and then moment about the x-axis, stick a y to it, moment about y-axis, stick an x to it, and then just calculate. By the way, this is also a good section. This is also a good section where we can review a lot of integral. Right, so now we have another example here, which is a lot better because we have a rectangular region, and the density is polynomial. So we expect to have a rational answer here. By rational, I mean if we put in a calculator, we should get a fraction. Right, mass. Calculate mass. X is between -1 and 1, y from 0 to 1. So that's easy. Now very promising because when the limit are constant, and if the function is separable, we definitely will use Fubini theorem. Right. Density function is 2 minus y. And then because we can use dy dx or dx dy, doesn't matter, I'll use dy dx. Integral for x from -1 to 1, and for y 0 to 1. Constant limit, function separable. So this one indeed we can use Fubini theorem. So group the y together, 0 to 1, 2 minus y dy. Group the x together. Yeah, much better. I forgot to change to rectangular, but that's never mind. I mean, that doesn't matter. Whatever the variable should not be a problem. So we have 1/2 by 1/2. I mean 1.5 by 1.5. We should write that as 3/2. And integral here just x from -1 to 1. So we have 3/2. And then x from -1 to 1. Put in 1, put in -1, 1 minus -1. So 1 plus 1 is 2. So 3/2 times 2, 3. Much better. So the mass is 3. Yeah. As mentioned before, when we do the calculation, no, this one with the density, so so with the calculate density, the mass is 3. Never mind. It's not a centroid. Right now we calculate moments. Moment with respect to x. I'm just sticking x to this. And that would be totally wrong. Remember, the moment about the x-axis, we have to stick a y to it. Because we mentioned about this, right? The moment about the x-axis, this is the x-axis. Whatever the point, the distance to the x-axis is the y values. So that's why we stick the y values. If this is the moment with respect to x. Regardless, this still is Fubini theorem. So group the y together from 0 to 1, y, 2 minus y, dy. And then we still have that, which is 2. So what if this integral and we stick how to write, okay, insert times open parentheses right, that is 2/3. And that is 2. So we have 4/3 moment about the x-axis. Moment about the y-axis. Still the same integral as the mass integral. But about the y-axis, distance to the y-axis is the x values. We should start with this example as the first example. Anyway, still Fubini theorem, right? The function is separable, a function of x times a function of y. So we still can group the y together. Right. The first one we already did, and that gives us 3/2. The second one is x squared over 2 from -1 to 1. We shouldn't even do that. The limit is symmetric, the function is odd. This one is 0 without any calculation. So we know that this is going to be 0. Those limits are symmetric and the function is odd. So this should be 0. Of course, if you put 1 in here and -1 in here for x, they're the same, but subtract that give us 0. So we have 3/2 times 0 is 0. Now, does this make sense? So think about this. This one has density of 2 minus y, meaning that the density only depends on y, right? Think about that. Density only depends on y. I'm looking for a ruler. Okay, not one. So, since the density only depends on y, everything on the same line here have the same y values, therefore have the same density, right? Now, if you have a point here and a point here, the density would be the same. Therefore, the mass should be the same. But it is equally distant. negative x, and this is x. So there's a point here and a point there. They will balance each other out, or cancel each other out, right? So the moment is equal mass times distance. The mass is the same because density are the same. The mass are the same because density are the same. The distance are opposite, therefore the moment of those 2 points are opposite. So a point here cancel a point there, and this one perfectly symmetric. They cancel each other out on each half. Therefore, the moment about the y-axis is equal to 0. And later on, the center of mass, the x-bar, is equal to 0. So we calculate the mass, we calculate the moments. Now just center of mass. As mentioned before, this should be the first example. That would be a lot. Make it a lot easier. Just a point of just the concept. We not try to trick each other using the integration by parts and all the complicated integral. Right. So x bar is the moment about the y-axis divided by mass. Y bar moment about the x-axis divided by mass. Moment about the y-axis is 0. Just make sure that the previous one is correct. And the mass is 3. 0 divided by 3 is 0. And moment about the x-axis is 4 thirds. Divided by 3 is 4 over 9. So center of mass, x bar, y bar is 0 and 4 over 9. Simple enough. Right. Now think about this. Because this one we have a density. If this one the density is constant, if the density is equal to constant in this problem, the center of mass will be right in the middle here. But it's not. This one the density is 2 minus y. So I will ask you, is that the top heavier than the bottom, or the bottom is heavier than the top? So think about this. The top here, y equal to 1. So the density is 2 minus 1 is 1. So the top here, the density is equal to 1. So on this line, density is equal to 1. Because 2 minus 1 is 1. Everything on this line, y equal to 0, and the density is equal to 2. So this one, the bottom heavy. The bottom is heavier than the top. So that's why the center of mass, instead of right in the middle, it tends to go forward to the heavier side. So by 4 over 9, so the center of mass is somewhere in here. Because the bottom is heavier than the top. But the left side and the right side, the weight are the same, cancel each other out. So the center of mass, the x bar will be right in the middle. So that actually makes sense. So that certainly works. So that's center of mass for 2 dimensions. Now we go to 3 dimensions. Will be the same. Now, so the center of mass, of course, rho is still density, all kind of that, but now x bar is the moment about the YZ plane. So different in 3 dimension is in 3 dimension. In 3 dimension, the moment about the XY plane is Z coordinate is the distance to the XY plane. So we say the moment about the YZ plane, moment about XZ plane, and moment about XY plane. And the mass and the moments as follow. For YZ, distance to YZ plane, we stick an X to it, and distance to the XZ plane, we stick a Y to it. And then at the moment, in general, if you forgot the moments. Whether double or triple integral doesn't matter. Let's say this is the mass. If you want to find, let's say, y bar, so those are the masses. For y bar, we just say the moment with the y to it. But technically, when we put the y to it, this one is said to be the moment to the xz plane. Yeah. So, in terms of the intermediate step where they find the moment, this could be confusing. But when we calculate the mass, there's nothing confusing about it. If we want y bar, we stick the y on the top, the bottom is the mass, we don't stick any variable to it. If we want z bar, we're going to put z in here. But if it is z, then that is the distance to, or the moment about the xy plane. Yeah, so the name for it may change, but if we want z bar, we have z in it. If we want x bar, we have x in it. We have y bar, y in it. Over the mass, would have no x, y, z in that. Right. Let's look at the first example. I'll find the center of mass of the cube. Negative 1 cross. Right. We haven't seen writing anything in this order, but actually this is a very common way to write. So we have an interval from negative 1 to 1 in the first dimension. So when we see this, negative 1 to 1, we can write x between 1, negative 1 and 1. 0 to 2, that is y between 0 and 2, and then z. It is a cube, so the length is 2 by 2 by 2. That makes sense. The density though, we have the density. Right. First, let's hope that we have enough space to do this problem. But look simple enough. Constant limits, function separable. Definitely Fubini theorem here. Right. Let's look at the mass. For triple integral, this is the volume. That triple integral. And for triple the region, usually we use D instead of R. But that's just some simple. Even better, we can just draw a cube, right? This is a cube. Just draw that instead of D. This a lot more descriptive. Then we have the density function. Sorry, I should write completely before I start talking or write something else. Right. So, triple integral give us the volume, multiplied by density, give us the mass. Density is y, and then dv, it doesn't matter. X, y, z, all of them are constant, so we don't have to worry much about the limit. When I have a choice, I usually prefer reverse alphabetical order. X from negative 1 to 1 is on the outside. Y in the middle, 0 to 2, and z in the inside, 0 to 2. Once again, for Fubini theorem, the limit are constant, function separable. So this definitely we can just group all of them on the axis, on the z and on the y. On the z we don't have anything but from 0 to 2 of dz. For y, we have the y though. And for dx from negative 1 to 1 dx. So this gives us y squared over 2 and put 2 in, so that is 2. So we'll have 2 in integral from 0 to 2 of dz is just z 2 my So usually when we integrate this, there's just 1 here, then we just subtract the limits. Subtract, so 2 minus 0, and then this is y squared over 2. That also 2. Right, so 2, subtract the limit, also 2. So the mass is 8. Now the moments. The moment with respect to the xy plane that is where we will distance to xy plane is z, and then the density function, everything else, so just y dz dy dx. Z is from 0 to 2, y from 0 to 2, and x from -1 to 1. For linear theorems again. For z, -1 to 1, and then z dz. I hope you recognize this. When we have this is going to be 0. Symmetric limits, an odd function, that cancel out, that should be 0. Don't need to do any further, but we want 2, 0 to 2, y dy, and then x. Never mind, the -1 to 1 is the limit for x. Sorry. So for z, that's 0 to 2. So it's not 0. Sorry about that. So for z, so now you know why I recommend that we write the limit equal to, so we don't know which one's which. So we know which one's which. So for z, limit from 0 to 2. So that's correct. Sorry about that. -1 to 1 is dx. And this is the same as that. We just switch the letters, right? And that we calculate already, which is 2. So this is 2, this is 2 because those integrals are the same. And this is also 2 because this constant. So we just subtract the limits. This is 1, so we just subtract the limit, which is also 8. So that's the moment about the xy plane. Now the moment about the xz plane, meaning we want to stick a y into this. We have -1 to 1, 0 to 2, and 0 to 2. With respect to the xz plane, the distance to that is the y values. And the density functions y, and then dz, z go from 0 to 2, dy, y go from 0 to 2, and x go from -1 to 1. Alright, let's group them. For z, 0 to 2, and there's no z here. And on the y, we have y squared. And on the x, so that gives us subtract the limits, that 2, second, enter, Just make it square. You know what? Actually, let's change fraction. A over 3. And the last integral is 2. Yeah, let's change this back to function so we don't have to see the theta in the integral, kind of weird. So 2 times, so that will be 4 times 8, 32 over 3. Right? Now the moment. Oh, this one's perfect. We have just enough space. With respect to YZ plane, meaning we're going to stick an x to it. Integral -1 to 1, 0 to 2, 0 to 2. Now we will stick an x to the mass integral y dz dy dx. Right. -1 to 1. This is what I mentioned before. Reverse alphabetical order. Just want to be consistent. Even though I realized if we jump right ahead, the integral with respect to x will be 0. But yeah, that comes later. Now, reverse alphabetical order. For z, 0 to 2. There's no z here. Oops. For y, and this time we have an x. Now this is what I was talking about symmetric limit, an odd function. So this would be 0. Yeah. Of course we can make it any odd function. Still 0. So we'll have integral here. It's going to be 2 when we subtract them. And we did plenty of that. 2. And the last one 0. So 0. So we calculate the mass and the moments. And then finally, x bar is what over the mass. So which one of them? Right. Now, even though the name of it's a little off when we have x and then yz, but if we want to find the x bar, we look for the integral that have x in it. So it's going to be this one. So in this case, it's going to be 0 over mass is 8. Y bar is a moment divided by mass, a moment that has y in it. So it's going to be this one, moment about the xz plane, which is 32 over 8, 32 over 3. Divided by mass is 8. Multiply reciprocal should be 4/3. So that's 4/3. And now the moment. The z bar is a moment that have a z stick into the mass integral. So moment about xy plane over m. So it will be 8 over 8 equal to 1. So center of mass is x bar, y bar, z bar, 0, 4/3, and 1. Now think about this. We talk about a cube. X between -1 and 1, y between 0 and 2, and z between 0 and 2. This density function only depends on y, meaning that the y bar will change. The y bar will not be in the middle, but the x bar and the z bar should be in the middle, because density does not depend on x values or z values. So the x value should be right in the middle of this. By the way, we're talking about a cube. If we talk about some parabola, some irregular shape like this, the center of mass, of course, I'm not sure where it is. But if we're talking about a box or something symmetric, then the center of mass should be, if it is symmetric, does not depends on a density function. It will be right in the middle, just like this, because the density does not depend on x, and this is a cube or rectangle, anything that is symmetric. The x value should be right between the x values. The y values will not be between the y values, because that's the density function. But the z values independent, the density independent of z, and this is a cube, perfectly symmetric about the x, y, and the z. So the z bar should be right in the middle of 0 and 2. So that makes sense. X bar is equal to 0, which is between -1 and 1. Z bar is 1, which is between 0 and 2. And y bar is 4/3, which is not between 0 and 2, because the density depends on y. So that should not be right in the middle. It's a little bit off. And for y, so for the bigger value for y, density is bigger, so it is heavier on the numbers with the high values of y. So that's why this is a little bit bigger than 1. Right. The next two might not be as simple, but I want to switch to something else. This one, find the centroid, so density is equal to a constant. But for simplicity, if we want to find the centroid, we're just going to let mass equal to 1. I'm sorry, let the density equal to 1. What we wrote earlier. Yeah. For simplicity, let that equal to 1 when we calculate the centroid. Yeah, the center of mass, whose density is constant. So when we find the centroid, that rho equal to 1. Okay. So for the centroid, density is constant, and since we find the center of mass, we can just let density equal to 0. Density equal to 1. Right. For every centroid problem, if we find the centroid, let density be 1, so that saves us some time. Now this is a lot more interesting, because we don't have like a cube, a little more complicated. We have a cone. So we gotta find mass, stick x, y, z into it, so just like what we did before. So for mass, it's going to be a cone. And then the density function is 1. And that's 1. And then just dv. Right. Now this is a triple integral, a bit more complicated. Right. So for this I have to figure out what should be the middle, what would be the inside variable. After that it will be easy, will be on the xy or the 2 planes. Since I have bounded by 2 functions of z, it would be wise to put dz in the middle. And if we look along the z-axis, we see this plane first, and then we see the diagonal plane, the sine of the cone. So z equal to 0 from the bottom, z equal to whatever that is. And then dz. On the outside, worry about that later. What will be on the outside though? As you see, it says that when this is on the xy plane, we just have this, which is a circle radius 4. And everything inside. So we just have a disk for xy radius equal to 4. Right. Yeah, certainly we can set up the limit for x and y. However, this is a disk, and the function here is xy plus y squared. So this is much easier if we convert everything to polar. So that is just r squared, and limit for that in polar is just this. So this one a lot better if we convert to polar. Convert to polar, the region R is going to be R between 0 and 4, and theta 2 pi and 0. So I mean I convert x and y to polar and I keep the z. So I should say convert this to cylindrical coordinate instead of polar. But if we just convert x, y, it's perfectly fine. Don't worry about it. Right? Let's go. So the mass. So in polar, x squared plus y squared here is equal to r squared, right? Square root x squared plus y squared is r squared. Yeah, we convert to polar, we can take care of that. Right, easy. Right, just one thing though. In polar, dA is r, dr, d theta. So don't forget that r. Right, limit for r though, 0 to 4. And limit for theta, 0 to 2 pi. So that is the mass. By the way, if this is just a cone which have the formula for a cone, we just go ahead and use it. But we do need the integral to find the moments later, so never mind. Still need to do this. This limit has the variable, so let's just rewrite that for square root of r squared. R go from 0 to 4, so this is positive. So just say 4 minus r r dr d theta. The r here we can write here, or we can write here, as long as it is within the integral of dr. We cannot write the r outside of it. Within the integral of r, we can put r anywhere we want. We can put r right in here if we want to. It doesn't matter, as long as between the integral of r. Right, inside integral, I will integrate with respect to z should write this one smaller because we might not have enough space. Oh, but it turned out to be very nice. Don't worry. Should have enough space. Change my mind. Yeah, the reason because this is centroid and it is perfectly symmetric, so look like x bar and y bar should be 0, right? Because it's symmetric in the cone and density is constant, so it should be somewhere in there. Anyway, put 4 minus r, we have something, put 0 and we have nothing. So even though we should have enough space, but I still write small. 4 minus r dr d theta. Now for beginning, we'll work on this one because limits are constant, function is separable. So this, we group the theta. And then we group the R. First one gives us 2 pi. What's that integral? over 3. 32 over 3. So that gives us 64 over. So mass equal to 64 pi over 3. So that makes sense. We know the formula for the volume of a cone. 1/3 pi r squared. This is the base area times the height. The base radius is 4. The height is also 4. That gives us 64 pi over 3. So that makes sense. Yeah. So this is the cone. 4 minus square root of x squared plus y squared. When we have x squared plus y squared, when x and y equal to 0, and 0, z equal to 4. So that's why we have the vertex. I mean the top of the cone is at 4. So the height is equal to 4. When we make this equal to 0, we have the base. The base of the cone is where z equal to 0. So that equal to 0. Move the 4 over and square both sides. We have x squared plus y squared equal to 16, which is the radius, the disk radius 4. Anyway, we have the mass. Now calculate the moments. Moment with respect to x. We know, sorry, there's no with respect to x anymore. With respect to the xz plane. So moment about the xz plane will be this integral. So which one should we choose? We will have to choose this one because this one we integrate already. So 0 to 2 pi, 0 to 4, 4 minus r, dz, r, dr, d theta. With respect to z, and with respect to xz plane, distance to xz plane, we're going to stick a y to it. But if we stick a y to it, this is the same as in polar coordinate. X equal to r cosine theta and y equal to sine theta, r sine theta. So instead of y, we're going to put r sine theta. Fy will be r sine theta. That is in polar. Or also, or you can say in cylindrical, same thing, right? It should be in cylindrical because it's 3 coordinates. Right. That is y. Still have dz, r, dr, d theta. Right. Now, I did mention that this should be 0, right? So how do I know that? First of all, let's write the d theta because sorry, not forbidden theorem yet because there's a limit, so never mind. There's no z in here, so integral with respect to z is r sine theta, z equal to 0 for minus r, and then r dr d theta. Right. So it is easier to see if we just integrate this, and that gives us this. Right. Now inside, we have r sine theta. Put this in for z, for minus r. That's it. R dr d theta. Now this forbidden theorem will work here because constant limit function separable. We can pull all the r together and all the theta together. First I pull the theta together. There's sine theta, right? And then all the r for minus r dr. This one equal to 0. Because from sine, cosine, it doesn't matter where we have sine or cosine here. 2 pi is the period. If we want one complete period, we have a part on the top, the part on the bottom. That will cancel out. So that's why this is equal to 0. For sine, cosine, if we will go one complete period, it is going to be 0. Yeah. So this is equal to 0 times something with still 0. Right. That is m of x, z. Now, m of, let's do y, z, meaning that the moment about the xz plane, I mean yz plane. Now we'll stick an x to it because distance to the yz plane is the x values. And the x is r cosine theta. Now we don't have to do this because this will work the same way. When bottom line, we after some calculation, we should have from 0 to 2 pi and cosine of theta d theta, which is 0 times something. Right? So pretty much just like this, but except we're going to have cosine instead of sine, and cosine is equal to 0. So this is equal to 0. Right? and then the moment about XY plane, where we're going to stick a Z into it. Right, now we focus on the inside integral, this integral. Integral with respect to z, that will be z squared over 2 1 from 0 and 4 minus r dr d theta. Right, put in 4 minus r here, we have something. Put in 0, we have nothing. So we have 4 minus r squared over 2 r dr d theta. Constant separable function, definitely for Forbigny theorem. First for theta, next for r 0 to 4 minus r squared over 2 r dr. Yeah, this section is a lot longer if we have to do all this by hand. Oh, 32 over 3. That sounds familiar. But the first integral is 2 pi. 32 over 3. So that's 64 pi over 3. That's exactly the mass. Right, so we have that. Finally, the center of mass. X bar is the moment divided by the mass. The moment that where we stick an x to it. So moment y z with respect to the yz plane, which is 0. The mass doesn't matter, will be 0. So that x bar. Y bar, the moment that doesn't have where we stick a y to it, so that is xz divided by the mass. Again, moment about xz plane is 0 divided by mass, a positive number, so still 0. And then the z bar, where we stick a z to it, so the moment about xy plane divided by mass. 64 pi over 3 divided by 64 pi over 3. They are the same, so when they divide, it's 1. So the center of mass, x bar equal to 0, y bar equal to 0, and z bar equal to 1. So the center of mass is 0, 0, and 1, which makes sense though, because x bar and y bar should be 0. The cone, the center of mass should be right in the axis of symmetry. So that's why x bar and y bar equal to 0. And then z, because this is the constant density, the base will be heavier than the top. So the center of mass will go toward the heavier side. So that does happen to be 1. Right. So It's not that bad. The concept is pretty simple. We calculate the mass, just the volume, stick the density to it, and then the moments distant to a plane or distant to a line, doesn't matter. We just find the distance to whatever the plane or the line is, and then just find the center of mass. Yeah, I just want to make this one in the cylindrical coordinates or polar coordinates to make things more interesting, but the idea, the integral is still the same. Right. I'm not sure we have enough space to do this one because that looks extremely long. Right. At least if we cannot finish this problem, at least we set it up. Right. I'll find the center of mass of the interior of the hemisphere of the radius A. So the radius is A. With the base is on the XY plane. So this is the upper hemisphere. The density is that. Right. So the mass. This is over the upper hemisphere. Yeah, that's what I mean. I'm trying to draw that. Then we have a function for density and then dV. However, this one, the density function given in the spherical coordinates. So we could be wise if we use the spherical coordinates. So for that upper hemisphere, the spherical coordinate rho, the sphere radius A, so we go from 0 to A, phi or phi from the z-axis down to the xy plane for the North Pole to the equator, that's 90 degrees. So we go from the top 0 to pi over 2, which is the equator, and then theta from 0 to 2 pi. Now the density here is depends on rho. So center of mass is somewhere in the middle. It might not be symmetry. Right. Now we know the limit is that. The function, the density function is 2 minus rho over A. In spherical coordinates. Don't forget the dV is rho square. In the next section we will prove this. Sine phi d rho d phi d theta, rho square sine phi d rho d phi d theta. The rho, the radius from 0 to A. For phi 0 pi over 2, and for theta 0 to 2 pi. So all of them are constant, so it's good. The function also separable, also good. Yeah, let's just find for this problem, let's just find mass and then one moment and one coordinate. That's all I mean. Doesn't look like I have enough space here. Right, mass. Certainly for Wiener theorem works a constant function, constant limits the function as separable. I can pull all the rho together and all the sine, all the theta or phi together. So first for theta, there's no function of theta. phi. Now what makes things complicated? Because here we don't have the constant. A just a constant, we have constant. But because there's A, we cannot really put this in the calculator. Cannot put A in it. So that one we calculate the mass. It's not that bad though. Integral here is cosine, and let's see from just do that. So give us 2 pi for the first one. For here, integral cosine is negative cosine, and this multiply in sine, and then 1 over a rho cube. So 2 pi, negative cosine of pi over 2, which is 0, minus the negative cosine of 0, which is 1. Integral here is 2 rho cube over 3 minus 1 over a rho fourth over 4. As we integrate from 0 to a. Check 2 pi. That is cosine of 0 is 1. Cosine pi over 2. Cosine of 90 degrees is 0. Put a in here, we have 2 over 3 a cubed. And put a here. That a to the fourth, but cancel with 1a at the bottom. So 1 over 4 a cubed. So 2/3 minus 1/4. (512). 2 pi 5 over 12. 10 pi over 12. So that gives us the mass. Got a feeling that we write too much and run out of ink. Right, so that is the mass. Now we calculate a moment. I said there may not enough space to do all of them, so I'm just do maybe 1, maybe 2 of them. Right, so that was the mass. Now the moment. Let's do the moment about the XZ, XY plane. With respect to XY plane, the distance to the XY plane, we're going to stick Z into it. The limit is still the same thing though. I'll stick Z into this integral. 0 to 2 pi for theta, 0 to pi over 2 for phi, 0 to a for rho. And then I have 2 minus rho over a rho square sine d rho d phi d theta. Right, but we cannot actually put z in it in polar coordinate. I mean in spherical coordinate, z is equal to rho cosine of phi. Right, If you don't remember that, remember that phi is come from the z-axis, and z adjacent to the angle, so adjacent is cosine. So we have rho cosine. Actually, we might do all of them. Right. For Bini theorem, because constant limit, there's no theta here. For phi, we have cosine and sine. And then we have 0 to a, rho times rho squared is rho cubed. 2 minus rho over a, rho cubed, d rho. Yeah, I just forgot the d phi in here. Other than that, that's all we have. Did the same thing. Not this. Right, sorry. So 0 to 2 pi, so that's just 2 pi, and I've just put this in the calculator. Cosine times sine is power reducing, so which is going to be 1/2 sine of 2 theta. If we want to integrate this by hand, rewrite that as sine of 2 theta divided by 2. Sine, cosine, is 1/2. And then that integral rho cubed minus 1 over a rho to the 4th. 2 and 1/2 cancel out, that's just pi. And then we can integrate 2 rho cubed, 2 rho to the 4th over 4 minus 1 over a rho to the 5th over 5. Evaluate from 0 to a. So we have pi times, put a in here, we have something, put 0 in there, we have nothing. So we have 1/2, 2 and 4 cancel out, a to the 4th minus a to the 5th, but cancel with h, so we still have 1/5 a to the 4th. So we have pi times 1/2 minus 1/5, over 10 a to the 4th. So 3 pi a to the 4 over 10. Right, so this is the z, we stick a z to it, so we can say z bar is m of xy over the mass. The moment about xy plane is where we stick a z to it, so we have 3 pi a to the 4th divided by 10 divided by the mass of 10 pi over 12. So 3 pi a to the 4th over 10 multiply reciprocal 12 over 10 pi. Pi cancel out. We have 36 over 100. Did I forget something? I did, right? Here we have a cube, right? So I forgot a cube. That's where I run out of ink and I forgot to write it. So the mass is 10 pi a cube. Sorry. And a to the 4 cancel on a cube. So 36 over 100, or 18 over 50, or 9 over 25. Or just 0.36. Yeah, 0.36a. So the x bar, z bar is equal to that. Right, so that is the moment about the xy plane divided by the mass give us the z bar. Right, like I said, we don't have a lot of space to do this problem, so we just find z bar. For the x bar and y bar, actually it's not that bad. So let's find the moment about the xz plane. That's where we stick y to it, right? So I'm going to write this again, but instead of sticking z to it, I'm going to stick a y to it. Right. Now, but in polar coordinates, what is y equivalent to? So in polar coordinate, if you go back, y is equal to r sine theta, right? But in the spherical, r is equal to z and r, the angle is here. So r is opposite to the angle, opposite, so it's going to be rho sine phi sine theta. So that is what y is. And we're going to stick y to it, so we're going to put that in here. That looks very complicated, right? Extremely complicated. Of course, we still be able to use Fubini theorem. So let's group everything with theta. So we have theta here, limit for theta, and that for theta. Now, did I mention anything about whether we have sine or cosine and the limits going for one period? This one equal to 0, right? So it doesn't matter what we have after that. This is equal to 0. So when we calculate, since we stick a y into it, we have m xz over m, which is the y bar coordinate. is equal to 0 over, doesn't matter whatever the mass is, still equal to 0. So if we calculate y bar is equal to 0, similarly x bar is equal to 0, because for x bar we're going to stick rho cosine of, rho sine phi cosine of theta. So whether we have sine or cosine, when it go one period, it is going to be 0. For example, since the period of sine cosine is 2 pi, right? So I can go from 6 pi, let's say from 3 pi to 5 pi. Yeah, so I have sine, but go on for one period. The length is 2 pi. That should be 0. Well, that should be 0, but this is the machine error. This is a very small number, e to negative 14, meaning times 10 to the negative 14, which is extremely small. So the calculator gives us there's some calculating error, but that should be 0. Whether we have sine or cosine doesn't matter, because the period is 2 pi. When it go one period, the sine cosine, the part above the x-axis and the part below the x-axis will cancel out. So that should be 0. So in this problem, x bar is equal to 0, y bar is equal to 0, and z bar is equal to that. Yeah. For the moment, with respect to the moment about the yz plane, instead of sine, we're going to have cosine here, which turn out to be 0 as well. Right. Yeah. So of course, in this section we only do center of mass. So find the mass first. The mass is the volume, stick the density to it, and then we find the moments. Whether we go into the line or whether we go to the plane, whatever the distance to that object, the moment about that object is the distance into the mass integral, and we just integrate, and then the moment divided by mass give us a coordinate, the average on that coordinates. Right. Yeah. So we did plenty of example. I think this is a good review of triple integrals, spherical, cylindrical coordinates, and of course we take advantage of Frobenius theorem whenever possible. Whenever we have constant limit function separable, we use Frobenius theorem. Just a quick check. If we have the integral something like this, even though the limits are constant, we cannot use Frobenius theorem here, because the function here cannot be separate in terms of function of x times a function of y. So two things need to happen in the Frobenius theorem: limits are constant and the function is separable. In that case, we split, and I will do that every time I have that chance, because that will simplify the integral by a lot. Anyway, so I said we did quite a few examples on this, so that covers a lot of integrals. So this is a good review. We have one more section in this chapter. The next chapter will make sense out of this. Why doing some certain spherical coordinates or cylindrical coordinate, sometimes why do we have to multiply that into it? Right. The next section will explain it. But that's it for this section. As always, thank you for watching.